I talked about spring mass model simulation. I kind of covered robot simulation uh, in a higher level. Now I'm going to get into more details and talk a bit more about the the parameters that use in simulation. So what we're trying to do is uh, kind of simulate the physical environment, the forces that are applied. So we are talking about the main forces. There are some like detailed forces that we skip for the purpose of getting the things right and being practical. And so in we're gonna talk about the main forces that are involved in simulating a robot. And if you have taken high school physics, a lot of this sounds familiar. So contact and friction are some major points that I am going to talk about today. We'll we'll kind of talk about visualization, collision, friction, contact, and some other constraint quickly in this video. If you want to handle collision with the ground, I kind of covered this, shortly, briefly in the previous video, but you need to apply a ground reaction force called, we're gonna name it F sub G upwards, once a node goes below ground, which means that its Z coordinate is less than zero. So how do we calculate that F sub G? F sub G doesn't have any X or Y coordinates, so therefore both of them are zero. In the Z coordinate, the F sub G has the magnitude of minus Z times K sub G. Minus Z is the amount, the distance it travels below uh, the ground. Ground plane is located at Z equals zero. So if it goes below that, then we have some um, value of Z, so negative zero, negative Z. We multiply by negative one so to have a positive value. And K sub G is actually the coefficient of the ground. So we'll consider the ground to be a spring like any other object in our simulation. And K sub G is the spring coefficient of the ground. So because the ground is usually very hard, so the K sub G is also very big, so 100,000, and we don't have, it's a unitless variable. That being said, so you can see that in this example, this object hits the ground, goes back up, as the uh, F sub G force um, exerted on this object upward. So that's why every time it hits the ground, it goes a little bit below the surface, below the ground, and it's just as long as it goes below the ground, it uh, goes back up. Um, when a mass is at or below the ground, you can simulate the friction and sliding. Assuming, so right now we're talking about uh, friction, right? So we assume mu sub s to be the coefficient of the static friction. So we have two types of friction. One friction is while the object is not moving and a force exerted on the object, but it's not enough to move the object. Until the object moves, right before the object moves, the coefficient of friction is static friction, which we call mu sub s. And when it starts moving, then the friction becomes kinetic friction, and we call it mu sub k. In order to calculate this horizontal force, the friction force that is exerted on the object, we call F sub h, we have to uh, get the square root of F sub x squared plus F sub y squared, and the normal force F sub n. Why do we need these two? Um, If F sub n is less than zero, in other words, the force is pointing upwards. Then if, so there's two conditions. In the first condition, if F sub h is less than, so the horizontal force that is uh, in the opposite direction of the movement, if it is less than negative or minus F sub n times mu sub h, which means before it starts moving, because if F sub h is less than that, then the horizontal force of the mass is zero, right? But if the F sub h is greater than or equal the F sub n times the coefficient of the static friction, then reduce the horizontal force of the mass by the kinetic friction coefficient times the force. Does it make sense? So until the object hasn't moved, we have this static friction, and when it starts moving, then we have to subtract the force that is the horizontal force that has been exerted on the object by the vertical force, the normal force on the object times the uh, static friction. And then the remaining is what's actually, uh, sorry, you multiply the normal force by the uh, kinetic static friction, kinetic coefficient of friction, and you subtract that from the force, and that is the resulting force that has been exerted on object. So then you use this F, this force to calculate the acceleration, or according to the velocity and the position and whatnot. Okay, so kind of overview of what friction is calculated, and this table kind of shows the coefficients of friction for common surfaces like steel on steel, aluminum on steel. We have both, the static coefficient of friction and the kinetic coefficient of friction. Mm. So this is how it's calculated. It's calculated by experimenting and recording the results. In terms of visualizing the object, one important point is that uh, you want to make the object look solid, because you have these spring mass objects that are, if you just show them as they are, they just, these look like these hollow objects that don't have anything. But you can cover them up, look solid, by shading all the exterior triangles of the robot. But you want to only shade the external triangles, because if you shade all the triangles, then you're going to have these computation time, computation complexity that's going to rise, because each triangle is going to add to the computation. So this cube is an example. Even though it's a spring mass object, the triangles on the surface are kind of shaded. And the same way as this, you can kind of see the triangles here. So that's about visualization. Um, but you also, let's talk about collisions a little bit. So you have different types of collisions. Some of them you have to handle, kind of take care of them, and sometimes some of them you have to ignore. The type of collisions you need to make sure they're handled properly is the mass on width triangle. Okay, and the other one is edge with edge. I'll show you, what they are in the next slide. And the other one that you can ignore is mass with mass, mass with edge, edge with triangle, and triangle with triangle. So if you consider this triangle, it has three edges, and there's a mass that kind of collides with this triangle. You need to handle this. You have um, springs that are connected to the point of collision, and these springs are supposed to take care of this collision. And when you only apply these springs when the collision happens. So right before then, there is no spring, but once the mass hits the surface of the triangle, then you need to add these springs and then calculate how it affects the dynamic of the object and the system overall. And then when the collision or when the mass exits the the triangle, you remove those temporary springs. And the other one is edge on edge. So these are edges that could have a collision. Again, the same way here, you once the collision happens, you add these temporary springs, uh, connecting the nodes of the edges. How they impact or how they're impacted. The springs take care of the impact dynamics, and then when the edges exit the collision situation, then the temporary springs are removed. Another important point is dampening. What is dampening? It basically means when the energy goes to waste by matter of friction. It's mainly friction because uh, when you're like, for instance, release a ball from a certain height and then you let it go, it goes up and down until it settles on the ground. That's dampening, right? Uh, there's a lot of uh, forces that kind of uh, remove the energy of the system by um, converting it to heat or whatever. But it's those the energy is useless. And you can see that the kind of graph that shows starting with some energy level and it's just going to zero over time. And you can do this by multiplying the velocity by some number similar to 0.999, and for each time a step you do that until it reaches zero, unless you insert energy into the system. Um, you see the energy level here again being dampened. You can also have uh, water of viscous dampening. So, for instance, if you're driving a car, the dampening of the speed is caused by a number of factors, including the friction, air friction, or the road friction, or whatever. So you can apply this drag force that is dampening the speed of the vehicle by this drag force that equals c times v squared in the opposite direction of v. So c is the drag coefficient, some constant, and v is the speed, the velocity of the object. So recently, uh, maybe 10 years ago, there's a concept of soft robots that have been evolved to run and to grow like plants. The way they are designed is um, you kind of have these robots that are made of these small particles, small elements, and these grow to be whatever they need to be based on the objective that is given to them. So I'm going to show you, play this video. I'm going to show you some examples here. These work written here by Cheney 2013 and Cruci et both are graduate at the time PhD students at Columbia University. Uh, so inspired by biology and how some of the organisms are designed to be efficient in the water. So this kind of similar, it is similar to stingray. And keep in mind that these are not designed directly, but actually designed by some evolutionary algorithms. You can check out the papers. There are some interesting papers that were referenced here. This is kind of a jellyfish, again, that the evolutionary algorithm came up with. And similar to these, there are so many examples here in this video. I just wanted to show you a couple. Okay, so that's about, we talked about friction, dampening, um, things like that, and also visualizing, and also collision. These are the topics that I talked about. Now, I'm going to talk about actuation and validation. Um, so, what does it mean by validating a model? So, if there is no dampening or friction, energy should remain constant. This is one way of validating the simulation. So, what we do is plot the total energy of the cube as a function of time. So we have different types of energy. We have the kinetic energy, we have potential energy due to gravity, potential energy in the springs, and energy in ground reaction spring. And if you add all of them together, they all have to remain constant. As you can see this in dark graph here, this is the sum of all the energies in the simulation. And if it is not constant, there is a bug. There's a energy leak, if you may. And you have to kind of find what is causing that. Here's another example that shows the energy level. Same here, showing soft body robots released from different heights. Showing the same robot, in the simulation, and also showing in simulation versus real environment. You can also, when you're simulating a robot, you can create constraints as you wish and as needed. One of the way of creating constraint is fixing mass at some x, y, z position. Or you can create a soft constraint, for instance, attaching a temporary spring between mass and a desired position. So it goes back and forth. That particular mass goes back and forth between that particular position and the length of the spring. You can set an anchor point by setting the v equals 0. If you set, like for instance, this point right here, as you can see in this video, this point right here has v equals 0. Or another way is constraint points to a curve or surface. You can, have that instead of having being fixed at one point, you can have it fixed at a curve. That point, moves around in that curve or a surface. That's also another way of doing it. One way of doing it is setting the Vx equals 0. So that means the velocity of that particular point in the x direction is 0. So it goes back and it basically can move on the YZ surface without changing the x coordinate value. How can we constrain a mass to a plane? If you have a plane equation given by ax plus by plus cz equals d, then I can, constrain a mass to a plane by this equation. So we set the force equal to k times the equation of the plane in direction of the a by c, ABC. Now, here's a question for you. How can we constrain the mass to a sphere? That would be your research. Um, so you can change material property, and one way is to set the spring constant to represent hard and soft material. As I talked about, for hard material, K is very high. So K equals 10,000. An example of a hard material, K equals 1,000 is a coefficient for a soft material. You can change K as a function of the spring length, like a non-linear material, and you can also change K with time. Uh, if you have a higher K, you need a smaller simulation dt. The time step has to be smaller because then because each time step the movement is going to be the force is going to be higher, the velocity is going to be acceleration is going to be larger. So by making the dt of time step smaller, you can capture the time steps between uh, each one of them. So another example of where the k is not constant is for cables. For cables, as long as your it's not straight, the k equals 0. Um, mm, so L sub L naught, which is the initial length of the cable, if you're not pulling on it, the k equals 0. But once you start pulling on it and it reaches that level, then k becomes uh, k naught. So if as it says in this bullet point, if k equals k naught, if L greater than L naught, and k equals 0 if L less than or equal L naught. And you can also have, some constant k that's variable. So for instance, with an actuator that with a rest length L naught that changes with time, you can set that, L naught to be a plus b times sine of omega t plus c, and omega is the angular velocity. Here's an example of an object where the k is not constant. So you can see these different, variable behavior by the object. Okay, thanks for tuning in. I'll talk to you later.